So the idea of completing the square. It's yet another technique that we can use to solve quadratics. Now, this particular one does actually factorise, I think, if I look at this closely. It does, yes. But let's pretend we can't. Oh, multiply together to give -7, add together to give 6. Oh no, I can't work that one out. So we'll do it via completing the square. Now, it's a systematic thing. We do the same steps every single time. When we complete the square, the first thing is move the constant. So we'll put that constant over the other side. So that becomes 7. Then we add half the coefficient of x squared. Now that pause is very important, because it's not half the coefficient of x squared, but half the coefficient of x squared. So the coefficient of x, in this case, is 6. Half the coefficient is 3. So we add 3 squared to both sides. Because what we're basically doing is, on the left-hand side, as the name suggests, completing the square. We're making it a perfect square. Because if I've got x squared plus 6x plus 3 squared, or 9, that's going to end up being x plus 3, all squared. So yes, 3 squared is 9, and the right-hand side becomes 16. So now we do factorise and get that perfect square. And so now we've got it in a situation where it's something squared is equal to a number, and so we know the solution is either plus or minus the square root of that number. So x plus 3 is plus or minus 4, giving me x is -3 plus or minus 4. So we get -7 or 1. So that's the idea of completing the square. And it is in fact where the quadratic formula comes from. Because as I say, those steps are the same every single time. Now if we do the same thing every single time, that's going to lend itself to a formula. And just to prove it, there you go, here's our general quadratic. It's a lot easier to complete the square on monics. So the first thing I'm going to do is divide everything by a. So I've got it as x squared. So what did we do? We moved the constant over. So minus c over a goes to the right hand side. Then we added half the coefficient of x squared. So the coefficient of x in this case is b on a. Half the coefficient then is b on 2a. And we'll add that squared. Okay. This left-hand side will become x plus b on 2a all squared, and over on the right-hand side we've got a bit of an algebraic fraction to do. Common denominator will be 4a squared. Starting to look a little bit familiar now. The numerator then becomes b squared minus 4ac. Well, that's what x plus b on 2a all squared equals. So x plus b on 2a must be plus or minus the square root. So we now have x plus b on 2a is plus or minus the square root of b squared minus 4ac, and the square root of 4a squared is just 2a. Move the b on 2a over, and we get our familiar formula. So that's how, in fact, they derived the quadratic formula. It's just actually completing the square. But they said, well, hang on, we're doing the same pattern every single time, so instead of doing it every single time, let's just create a formula to save ourselves some time. So x squared minus 6x plus 6. Here's another way I can think about it. It's an alternative way of looking at the perfect square. Is I just ignore the 6. I pretend it's not there. And I go, well, x squared minus 6x, if that was going to be a perfect square, I know it always factorises to be x and then half the coefficient of x, all squared. So I know it's going to be x, half of -6 is -3, so I know it'll end up being x minus 3 all squared. However, if I was to expand that out, I wouldn't get plus 6. I would get 9. So, in order to get 9 to 6, I have to subtract 3. But what I now have is the difference of 2 squares. Yes, it will involve a surd. So if it's the difference of 2 squares, I can say, well, x minus 3 plus the square root of 3, x minus 3 minus the square root of 3. And so therefore, x is 3 minus root 3, or 3 plus root 3. That's an alternative way of setting out the completing the square idea. So one eye is on our completing the square.